Okay, now we are still in section 5-3, and this is recording number 3. Okay, so let's read this example, 520. Survey. Public opinion reported that 5% of Americans are afraid of being alone in a house at night. You have a random sample of 20 Americans is selected. Find these probabilities. And he wants you to use the binomial table. So you got all these problems here, A, B, and C. All right, so the first thing, if you saw this problem on an exam, or in real life, if you're working somewhere and you had a problem like this, you'd say to yourself, well, is this a binomial probability distribution? Can I use the binomial formula for this? Well, there's a nuance here, and like I said before, they're not independent, because once you pick somebody, once you pick the 20 Americans, you're not putting them back every time you pick one, so it's not really independent. However, since 20 is a very small number, 20 Americans is a very small number compared to the entire population, we just say it's good enough. Now, I should mention to you, let's suppose it wasn't good enough. Let's suppose that you did not have a small enough sample, changing the problem completely. Is there a solution? Yes, there is. It's called the hypergeometric distribution, which we're going to see in the next section. So if you consider them to be independent or close enough to being independent for government work, we use the binomial distribution. If they're not independent, if we do these without replacement and they're not independent, okay, if they're dependent, what do? We use the hypergeometric distribution, and that's in the next section. So I want you to be aware that there's just another path that we would go down if we have to. Okay, so here's the formula that you would use to answer these questions, right? And as I say, if you use the formula, make sure you write it down each time. However, in this particular problem, the author wants us to do it by the table. So we're going to use the table. I'll do at least one of these, okay, just to make sure you got the hang of it. All right, so there's exactly 5 people. I claim that P, the probability of success, let me read the problem. There are exactly 5 people in the sample who are afraid of being alone at night. So that's a success. The probability of success is 5%. That was given to us up there. N is 20, because that's what we said right here, that there's a random sample of 20. So we have everything we need to know to do this problem. We know that N is 20. We know that P, the probability of success, is 0.05, that's 5%, and X is what we're looking for, that's the probability of X. So we could use that formula, okay? However, we also want to learn how to use the table, so let's use the table. Hopefully I can get it here. There we go. All right, so the N is 20. Let's go down here, keep going down. This is in the back of your book. Okay, so here's N is 20. X is 5, so that this column is N, this column is X, this is the number of successes. We want to know what the probability of 5, exactly 5 being successful, and P is 5%, so that's 0.05. So the probability of getting exactly 5 out of 20 successes is 0.002. And I'm happy to say that's what the author got as well, 0.002. Okay, so using the table is no big deal. I hope you'll agree. There's a couple of little nuances here. When we say there are at most 3 people, well, at most means there could be 0, there could be 1, there could be 2, or there could be 3. So that's why for problem number B, we have to figure out each one of these. But that's no big deal. You just use the table more than once. Okay, so I hope that helped you understand that. Okay, let's take a look at the next one. 5-21. It says that 70% of single vehicle traffic fatalities that occur at night involve an intoxicated driver. If you have a sample of 15, so N is 15, find the probability that between 10 and 15 inclusive, accidents involved drivers who were intoxicated. Okay, so N is 15. Probability of them being intoxicated, the probability of a success is 70%. There it is. That came from our given. And the X that we're looking for, remember, X is the number of successes. The number of successes that we're looking for, it says right here, between 10 and 15 inclusive. So it's 10, 11, 12, 13, 14, and 15. Okay? So here's the X's, 10, 11, 12, 13, 14, 15. So using the table, you just crank them out, and then you add them up, and that gives you what the answer is, 0.723. So roughly speaking, 72%. So if you pick, if you have 15 accidents, fatalities, 72% of them will be between 10 and 15. So, I don't know how else you want to interpret the data. You could interpret it a couple of different ways. You might say, well, I'll leave that to you. Okie dokie. All right, so now here's the key thing here. This is very important. All right, the mean, variance, and standard deviation for a binomial variable can be found by using the formulas in section 5.2. We can use those formulas, those horrible formulas that were so hard to figure out. However, one of the big advantages of the binomial distribution is a very, very easy way of calculating the mean, the variance, and the standard deviation. So this is, among other reasons, this is one of the reasons that if you possibly can make a problem into a binomial experiment, you're happy because things are easy to compute. All right, so here it is. Here's the formula. The mean, variance, and standard deviation, if it has a binomial distribution, then here's the formulas. The mu, the mean, is n times p. Very, very simple, right? Sigma squared is n times p times q, and then the standard deviation is just the square root of that. So that, I mean, how could you ask for anything easier than that, right? Okay, so from example 5-22, we did that example before, I believe. We had the 4 coins. Let me just double check, make sure that was the same problem. Give me 1 second, because sometimes the ebook is a little bit different from the printed version. So give me 1 second. Okay, I'm sorry, folks. I guess I kind of got. That's why I don't like the ebooks for this reason. It's really hard to keep track of where you are in the ebook as compared to a paper book, in my opinion. In any event, so let me just start all over again. Example 522, tossing a coin. Okay, we're going to figure out these various things here, the mean, the variance, and so forth. You toss the coin 4 times. Find the mean, variance, and standard deviation. Now, you could use that formula that we used before, and that was, you'd come up with the same answers. However, it's just hard. It's just too hard. We're going to use this shortcut formula. And it's a true fact that these formulas work for the binomial distribution. So, n is 4, p is 1/2, q is 1/2. So we're talking about heads as being our success. So the mean number of heads is n times p, which is 4 times 1/2, which is 2. So that's the mean, that's the mu. Now, coincidentally, as we've discussed previously, that's also the expectation. The expectation is also the same formula as the mu. And, expectation is kind of, what do you expect? Well, isn't that what you expect? If you flip a coin 4 times, don't you expect to get 2? Kind of makes sense, right? Sigma squared, NPQ is equal to this. That gives me 1. The square root is the standard deviation. That is equal, square root of 1 is equal to 1. So the mean is 2 heads, the variance is 1, and the standard deviation is 1. So you could use Chebyshev's theorems to kind of draw all kinds of conclusions from this without knowing anything else about what we're doing here, okay? All right, so now he's going to talk, we're going to use example 5.2. That's one we just did. When 4 coins are tossed many, many times, the average of the number of heads that appear is 2. So you do that experiment a bazillion times. The average of the number of heads that appears is 2. So you flip a coin 4 times. Flip a coin 4 times. Flip a coin 4 times. You do that over and over and over again. It's going to get closer and closer and closer to this so-called theoretical average here, okay? All right. So as stated previously, this problem can be solved by using the formulas for expected values. Here's the distribution, okay? So Um, this is using the formula that we learned earlier. Here's the formula. As you can see, it's a little more complicated. So I vote we use these simple formulas that the author has given us. Okay, rolling a dice. Okay, an 8-sided die. So that's that's not a die that you use playing craps in Las Vegas. It might be a game, a die that you use in a board game of some sort. Okay, so you roll it 560 times. Now, would you want to use this formula? Would you want to use that formula? Probably not. You would probably want to use this easy formula because it's just instantaneous. Find the mean, variance, and standard deviation of the number of 7s that will be rolled. Well, the probability of getting a 7 is 1 out of 8. There's 8-sided. It's an 8-sided die. So n is 560, p is 1/8, 1 over 8, q is 7 over 8. So NP is 70. So the average number of times, and the expected number of times that you will get a 7 out of the 560 is 70. So 1/8 of the time you're going to get a 7. Well, how many times is that? 1/8 times 560 is 70. That's what you expect. But you're not always going to get that. See, that's the whole concept behind deviations, standard deviations and variances. You're not always going to get that. Not always, okay? Sometimes you'll get 70. Sometimes you'll get 71. Sometimes you'll get, 68, okay? How is it dispersed? What is the measure of dispersion? Well, that's the sigma squared, or sigma. That's the variance or standard deviation. You crank that out. NPQ gives me, for sigma squared, gives me this. Sigma gives me 7.826. So if you were, for example, if you were saying, using Chebyshev's theorem, you might want to say something like, hey, within 2 standard deviations, I know I'm going to get 75% of the results. So mu plus 2 standard deviations, plus or minus 2 standard deviations. So it's going to be 70 plus or minus, 2 times 7.8. So let's just round that off to 8. 2 times 8 is 16. So 70 plus or minus 16, that's 86 and 54, right? Yeah. So between 54 and 86, 75% of your results will be in there. Okay, so it's kind of a quick and dirty way of seeing, what are you going to expect? Okay. All right, intoxicated drivers, same thing. We just did that problem, and we're gonna. Oh, I'm sorry, it's a different problem. 65% believe they should go to jail even if they have not caused an accident. We can do this calculation here, okay? All right, so that's it. That's the third. That was the third video. Each video takes about 15 minutes, so you can see I'm blasting through these really quick, but I'm trying to be as detailed as I can. The advantage of a video, of course, is you can stop it, you can rewind it. Also, because it's on YouTube, it has automatic captions, so if that helps you at all. So, I always recommend applying the concepts. I think it's very useful. You can look at some of the exercises for section 5-3. At least look at them. You don't necessarily have to do them, but at least look at them to try to come up with some good examples that make sense to you. Okay, so that's the end of section 5-3. Next section is 5-4, and the section 5-4 are some other types of distributions that we're going to also be learning about.